let's start off. All right, so we're looking at projectile motions. All right, so projectile motion entail objects that are moving in air that have both x and a y component. So they're moving both in an x plane and in a y plane. All right, so projectile motions are slightly different from free falling objects because free falling objects only occurs in your vertical plane, right? But for projectile motion, it occurs both in vertical and horizontal plane. So examples, we have shooting a basketball, playing golf. All those options, objects go up to a maximum and then fall back down in both planes. Now, we have different ways in which objects can move in a projectile motion. All right, so a full movement of a projectile motion is in a parabolic motion, meaning if it starts from a bottom, goes to the top, and then falls back down on the next side. While for this case, we're looking at if it's actually starting from a top height, and then we're allowing it to fall down to the ground. Right, so starting off, if this object is pushed off a cliff, right, in a horizontal motion, then the initial velocity that it starts off with will be v naught in only the x plane, right? So there's no rise in it, it's just being pushed off from the height in the x plane only, right? So in that case, we notice that the ball here falls in a curve-like motion until it hits the ground. All right, so it gives us that little curve there. All right, so at this point, we know that the object is accelerating because it's falling in air, so therefore gravity is affecting it, so it's accelerating. The acceleration is constant and is downwards, right? So gravity is acting downwards, so therefore the value never changes, so it's a constant acceleration and it's always acting down. So that means A is equal to G, which is negative 9.81 meters per second squared. The horizontal component of velocity is constant. All right, and does anyone know why we state that the horizontal component in projectile motion is constant?
Because acceleration is zero.
Because acceleration is zero in the x. All right, so why would acceleration be zero in x plane?
Because acceleration does not act in the horizontal direction.
Yes, so what reason would that be though? All right, so let me help you out.
Because it's constant.
Because it's constant. All right, what's the force that's causing the object to travel in a projectile motion? Which force causes it to travel in a projectile motion? All right, so the force that caught drag, all right, so that's a resistive force, and not really drag I'm looking for, but the force that causes object to fall in air in a projectile motion is gravity, right? And we know that gravity only acts in the vertical plane. So if the only force that's acting on the object is gravity in the horizontal plane, so that means your constant, or in your vertical plane, sorry, so your horizontal plane, the force there is constant. So the net force there is zero, so therefore there is no acceleration there, right? Because the object is only going either up or down because of gravity, right? So there is no net force acting on the object in a horizontal motion, so therefore the velocity is constant. Right? So therefore, at any point of this motion here, the horizontal velocity of the object will always be the same value. Right? So the horizontal and vertical motions are independent of each other, but they have a common time. Right? So that's saying that horizontal, vertical motion of the ball at any point, horizontal does not affect the vertical. The only thing that they have in common is that the time will be the same at each section. All right, so these are things that we just did. All right, so question, what is the trajectory? What is the total time of motion? What is the horizontal range? All right, so those, and what's the final velocity? So let's look at that. So remember, we started from a height. We're going to call that height h. All right, and we allow the object to be pushed off in a horizontal motion. So because of that, the acceleration in the x plane we know is 0 because the net force is 0. In the y, we know that it's g, which is negative 9.81 meters per second squared. For the velocity in your x plane, velocity in your x plane is equal to the initial velocity of the ball. And in the y plane, it would be g times t. And g times t is given because we know that acceleration is equal to velocity over time. Right? So therefore, v in y would be the g times the time. So at each time, then the y velocity will change. Right? And then the displacement. So for your x displacement, we know that speed is equal to distance over time. So distance is equal to the speed times the time. So the speed, which is your original speed at any point, is the same times the time it takes to reach at that specific point. And that x displacement is from where it was started from to the specific time that you want to check it for. And then for your y displacement, at any to find where how high the ball is at any point, then y is equal to h plus half gt squared, which is taken from the equation s equals ut plus half at squared. The ut, u times t, is actually distance. All right, so in this case, because it started at a height h, the ut there is the h that is actually started from. All right, so if it has started from the ground, then ut in this case will be different because it's not the height that it's starting from. All right, so is that clear? Any questions for this? All right, no questions, so let's move on. All right, so the trajectory of the projectile motion. All right, so we know that the distance that it traveled in x is equal to v naught t. The distance traveled in y is h plus half gt squared. If we eliminate the t's, all right, so we make t the subject in x equal v naught t. All right, so we have t is equal to x over v naught, and we substitute that in the second equation. What we get there gives us the trajectory of any projectile motion, and the trajectory tells us the shape in which the object is moving in. Right? So that's how you prove that the projectile objects move in a parabolic motion. Right? Because parabolic equations is basically y is equal to ax squared plus h, or ax squared plus any constant. That's the equation for the general parabolic path. All right, so the total time that it will take. All right, so we use the y equal h plus half gt squared again. So if we need to find the total time, then the y is 0. And the y is 0 because it's hitting the ground, so there is no height there present. So y is 0 plus h, which is your initial height that is falling from, plus half gt squared and half gt squared, yes. So we're finding the t, right? So we make t the subject, so we get the square root of 2h over negative g, which is the same as the square root of 2h over 9.81 meters per second squared. Right? So the h there only if the object is moving at an initial height. So once it's been projected from an initial height, to find the time it takes to complete its path, it will be the square root of 2h over negative g. All right, is that clear? All right, let's move on. All right, so the the range, which is how far from the initial point that it's being projected to the final point in a horizontal motion, right? And that's given by x is equal to v naught in delta t, right? So the change in x is your range is equal to your initial velocity in your x plane times the time it takes for it to complete its entire journey, right? So we can substitute both equations. So we get the range equals to v naught times the square root of 2 8, sorry, over negative g. And that gives us the range in which the object will move in your horizontal plane. All right, so also the final velocity in terms of before it hits the ground in your y plane would be v is equal to square root of v naught squared plus 2h times negative g. All right, so we're going to use these equations in some questions. All right, so let's look now at if, in this case, the object is actually projected from the ground up. All right, so if we project it from the ground up, it will always start from a angle, an initial angle, right? And we know these things. So your x and your y initially would be 0 because it's not moving yet, right? And your initial velocity vi is equal to the vi of your angle, right? So if we need to find the x component of your initial velocity, it would be vi cos theta. If it's your initial velocity in your y plane, then it's vi sine theta, right? And it's given by that little triangle created there. So sine and cos to give us the x and the y component. All right, so we know that motion is accelerated in your y plane. Acceleration is equal to g. Your horizontal component of x is constant again. The horizontal and vertical components are independent of each other, but with a common time. So let's look at these equations now when it started from the ground up. So in this case, your acceleration in your x is 0 again, in your y is equal to g. Your velocity in your x would be vi, so your initial velocity cos theta. For your y, it's vy is equal to vi sine theta, right, plus gt, that's your vy at any point. And then your displacement would be x is equal to vit cos theta, and your y displacement would be vit sine theta plus half gt squared. Right? That also tells you your trajectory. Even for a complete parabolic motion, you get that equation there. Looks like the quadratic equation, y equals ax squared plus bx. All right, and the total time for when it's a full parabolic motion, it's 2vi sine theta over negative g. All right, remember g is negative 9.8, and your total range would be 2vi squared cos sine theta cos theta over negative g. So sine theta cos theta is the same as sine 2 theta. All right, so we also know that the initial angle that for projectile motions, for you to get your maximum range away from the initial point of projection, the angle should closely be to 45 degrees, right? So that gives us a maximum in your range of values for your range, all right? So we know these things, right? And also when it's starting from the ground up, your maximum height would be your initial velocity squared sine squared theta over 2 times negative g, right? So all those equations there, we have been through those equations, right? So let's look at some questions here. All right, so here we go. So question 1. A ball is to be kicked so that the highest point of its path is just clears a horizontal crossbar on a pair of goal posts. The ground is level and the crossbar is 2.5 meters high. The ball is kicked from ground level with an initial velocity of 8 meters per second. Part A, calculate the angle of projection of the ball and the distance of the point where the ball was kicked from the goal line. Alright, so the first thing here is that we're going to look at what we were given. Right, and in this case, we were given the maximum height. The maximum height there is the 2.5 meters. We were given the initial speed. So we're given v naught, which is 8 meters per second. All right, and we can do a little sketch here. I show that it started from the ground, went to the maximum height, then back down here. Right, so we're given this, and we're asked to find this angle theta. All right, so in that case, what equation would you think would use in order to find the angle given based on the two values that we have? Anyone? Any equations you think would use in this case? I'm not seeing any answers from anyone. So the equation that we will use is the one about your maximum height, since we're given that, right, which states that maximum height h is equal to v naught squared times sine theta over negative g, 2g, sorry, right? So that's the equation that we will use. So we're given the maximum height, which is 2.5, equals v naught, which is 8, and we're squaring 8, times sine squared theta, which is unknown, over 2 times 9.8. Right, so that's what we do to find theta. So let's simplify this. So we get 2.5 equals 3.27 sine squared theta. We divide by 3.27 on both sides, and we get 0.76 equals sine squared theta. So to get rid of the square, we square root both sides. So sine theta is 0.872. So therefore, theta is equal to the sine inverse 0.872, which is theta is 60.69 degrees. All right, so is that clear for finding theta there?
Yes, sir.
All right, so that's the angle of projection, and then the next part says the distance of the point where the ball was kicked from the goal line. So what's asking us to find is that this here is where the goal line is at their maximum height. So we're asked to find this value x, right? So in that case, we can use our range equation. Right? So we now can add our angle, which is 60.69 degrees. So our range equation here, using our angles, would be x, which is your range. Let's use r, just to not get confused. So r is v squared sine 2 theta over g. All right, so what we're asked to find is basically half of r, because this is half of the total r right here. So we can have r over 2 equals r. Let's find r first, just to be simpler. Right, so r is equal to v squared, which is 8 squared sine 2 times 60.69 over 9.8. All right, I'm going to put all that in the calculator here. So that's 64 times. All right, so when we put all this in the calculator, we get R to be 5.58 meters. All right, so if R, which is the total length here, is 5.58, then that means X is equal to half of R, which is 5.58 over 2, which is 2.79 meters. Right, and that would be your answer for the distance where the goal line is. Right, and then the next part B says calculate the horizontal velocity of the ball as it passes over the crossbar. Right, so our horizontal velocity here, right, which is the same horizontal velocity at any point because that velocity is constant. So in that case, we can find the velocity, which is, so Vx at any point is V naught cos theta, right? And the V naught is 8 and cos is 60.69. So therefore, at that point, it would be equal to, which is equal to 3.92 meters per second. Right? And that gives us the x component in our velocity at any point. So it would be at the point where it passes the goal line. All right, and the last question for question 1. For how long is the ball in the air before it reaches the ground on the far side of the crossbar? So now we need to find the time it takes for the full trajectory of this ball. All right, so if we're finding the total time it takes, we can also use this equation. It states that time is equal to 2v naught sine theta over g. Right, so the 2 times v naught, which is 8 times sine 60.69 over g, which is 9.8. And that gives us the answer to be 1.42 seconds. And that's the time it takes for it to be kicked and for it to fall to the ground on the next side. All right, so are those working out okay with you guys? All right, no questions. All right, so the time is going to finish now, so we're going to restart before we move on. All right, so restart it now. All right, so let's look at question 3. So question 3 says, a ball is thrown horizontally from the top of a building as shown in the figure below. The ball is thrown with a horizontal speed of 8.2 meters per second. The side of the building is vertical at a point P on the path of the ball. The ball is a distance x from the building and is moving at an angle of 60 degrees to the horizontal. Air resistance is negligible. For the ball at point P, show that the vertical component of this velocity is 14.2 meters per second. All right, so vertical component means your y component. All right, so we know that our x component of this is 8.2 meters per second. We know that the angle theta is 60 degrees. Right, so we need to find our x component or y component, sorry. Right? So in that case, we can use, if we look at this figure given here, so we have 60 here, right? Your x component would be right here, which is 8.2 meters per second. So that means if we find this side, this gives us our y component is going down, right? And this is opposite to your angle. We have the adjacent of that there, so we can use tan, right? So we can say that tan theta is equal to the opposite side, and the opposite side here is your y component over your x component, right? So it's tan 60 is equal to the y, vy unknown, over vx, which is 8.2. So vy would be equal to 8.2 times tan of 60. Right? And when we do that, we get
14.2.
14.2. We get the 14.2 that is, right? So your y component of your velocity is proven to be 14.2 at the point P. All right, next part says determine the vertical distance through which the ball has fallen. All right, so what we're finding is the height at which from the top of the building to point P. All right, so let's add what we have here. So Vy we now find is 14.2 meters per second. All right, so we're finding this distance. So this is your building. Ball is going down like that. That's point P. So we're finding this height right here. All right, so anyone knows what equation we can use for finding the height? If we have the angle or both components of the velocity. All right, so we don't have the time. So I think we should be able to find time if we're given. All right, so we can find the time because we know that Vy is equal to V naught sine theta plus GT. All right, so we have V naught, Vy, sorry. So we can find V naught because we have both components. We have the angle, we know G, and we can find the time there. So first thing is to find V naught, right? And because it's both components, we know that's Pythagoras theorem. So it's a square root of 14.2 squared plus 8.2 squared. And that gives us 16.40 meters per second. All right, so we can substitute now. So this is 14.2 equals 16.40 sine 60 plus 9.8 t. All right, so that gives us, so 14.2 is equal to, this shows that we're going to get 0, which shouldn't be the case. Let's see if I did this right. Oh, yeah, sorry, the equation that we used was not the one that we should. All right, so we can use Vy squared is equal to V naught y squared plus 2gy. And that's given from the V squared equals U squared plus 2as. Right, so we know that Vy is 14.2, we square this. V naught y is initially what y component is, but it only moved in the horizontal initially, so that means V naught y is 0. Right, so 0 squared plus 2 times 9.8 and y. Right, because we're finding the y, which is the 8 right here. So the distance that it moved. So that is 14.2 squared, 201.64 is equal to 19.6 y. So therefore, y is equal to 2064 divided by 19.6, which is 10.29 meters. So that's the distance that P is from the top of the building in your y plane. All right, so is that clear for that question? All right, so the next part is to find what the distance, horizontal distance x is. All right, anyone remember the answer that was here? 10 point. No one remember the answer just given? Because we're going to need it.
10.29.
Okay, so y is 10. All right, so we need to find x. All right, so we know that x, sorry. So we know that x is the, we know that x is equal to the vxt. All right, so we have vx, but we don't have the time, so we have to find the time it takes for it to fall from the top of the building to point P. All right, so we know this, so we can use this one that says the y is equal to vy naught t minus, which is plus half gt squared. So the y here is the fall that it made, which is 10.29 equals v naught. Again, the vy naught, it's only in the x plane starting, so this is 0 plus half of 9.8 t squared. Half of 9.8 is 4.9 t squared equals to 10.29. So divide by 4.9 on both sides, and we get 2.1 equal t squared. So therefore, t is the square root of 2.1, which is 1.45 seconds. Right. So the time it took from the ball to travel to point P is 1.45 seconds. So now we can find what the x displacement is. Right. So we know that x is equal to vx times t. So the Vx is 8.2 and the time is 1.45. So we get 11.89 meters. And that would be your X displacement. All right, so that's enough practice with our equations using projectile motion. So it's just to remember the equations, right? And know which one to use if it's a half journey, just like this one, or if it's a full journey, like the first question that we did. All right. So those are the two options that we focus on with projectile motions. We've done two questions to cover those areas. All right. So let's move on to another topic, which would be momentum and impulse. So momentum and impulse. All right, so these are the things that we're going to look at. So we know based on Newton's second law of motion that F is equal to ma, right? So A is the change in velocity over time, which is noted as dv over dt, right? So we can show that the change in mv, which m times v is the momentum of the object in respect to time, gives us also force. So linear momentum is the effect of objects moving in the same plane, right? So it only happens in one plane, that's linear momentum. You know, units is kilogram meters per second, or sometimes noted as Newton seconds. All right, so impulse. So impulse, which is a capital J, is the product of the average force and the time interval during which the force acts. So what impulse is, it tells us that objects that are moving, right, if they collide, the force that they act on the other object with respect to a small change in the time for it to hit and release from that object, that is known as impulse. So it's the force that it strikes the other object with in respect to the small time that it takes to hit and release from the object. That is what impulse is really is. And impulse is a vector quantity, so it takes into consideration the direction. Right? And the impulse has a unit of Newton second because it's equal to force times the change in the time for impact. Right? We know that momentum P is equal to mass times velocity. Right? And also impulse can be given as the change in momentum. So it's your initial momentum minus the final momentum. Right? So also for momentum, there is also cases where you need to know about the impulse graph, which is your force times versus time graph. So your force versus time graph tells us what happens to what's the change in force over a period of time for object that is moving. All right, the area under that graph tells us the impulse of the object. All right, so if you have a graph of force times time and asks you to find impulse, you basically will find the area under the graph, right? And in this case, this graph, it resembles the shape that you use to find this one would more likely be a triangle, right? So even though it's a curve, it would be an estimated impulse because you're going to use the equation of a triangle to find the area of that section. All right, so example here, suppose the impulse J is equal to the integration of F due to time, shown in this figure as a value of 1000 Newton seconds. So the impulse is 1000 Newton second, which is imparted to an object of mass 50 kilograms, initially at rest. What is its final velocity? So we know that J is the change in momentum, right? So the J is given, which is 1000, right? We know the mass, which is 50. So the change in momentum would be your velocity, your final velocity 1, and then your minus from your initial velocity. Right? So remember the initial velocity in this case is 0 because it's at rest. So basically what we have is the impulse is equal to m times vf because the p initial is 0 because it's at rest. So in that case, F will be equal, so your VF will be equal to your impulse over your mass. Impulse is 1,000 over 50 mass, which gives us 20 meters per second. Right? And for collision, we are aware that we have two main types of collision, which is your elastic collision as well as your inelastic collision. Your elastic collision where objects when they collide they bounce off each other, and in those cases the total kinetic energy of the system after collision is equal to the total kinetic energy before the collision. In inelastic collision, the total kinetic energy is not conserved, right? Because the objects stick together after collision, so that's the reason why it's called inelastic. It's not conserved because that sticking effect causes kinetic energy to be lost to other forms of energy. So the principle of momentum, says that during a collision, your momentum before is equal to your momentum after. So it's just conserved and remains constant. All right, so for linear momentum, which we have been through before, we know it's just mass times your velocity because it's going in one plane. So all your values will be just mass times velocity as shown here. So we have a blue ball going to the right, we're going to collide with a bigger brown ball going to the left. After collision, they both stick together and move off to the right. All right, so in this case, we know that this is an inelastic collision because they're sticking together after collision. They're all acting in just the x plane. So it would just be your mass of your first ball times your velocity of the first plus your mass of the second times velocity of the second equals to the after collision. They're sticking together, so we add the masses and multiply it by the common velocity. All right, then remember that momentum is a vector quantity, so it regards your direction based on velocity. So if your velocity is going to the left, just like v2, then it gives you a negative value. So that's why we have a negative 1 meters per second squared there. Right, v1 is going to the right, so it's a positive velocity. So we retain a positive answer there. All right, so we substitute the values to find the VF, which is 0.125 meters per second. All right, so we're not going to actually focus on linear momentum because that's something that we have done before. All right, so we're going to focus now on, sorry, momentum that is not linear, so that means it's acting in more than one plane. So instead of just acting in your x plane or all in your y plane, they both act in x and y plane. All right. So in this case, we have the blue ball moving towards the brown ball, which is stationary, but it's moving in your x plane only. But after collision, the blue ball actually moves in a diagonal manner upwards, while your brown ball moves in a diagonal manner downwards. They both create an angle in your horizontal. For the blue ball, it's theta, and for the the brown ball, sorry, it's another angle there. So in this question, the momentum before will only be due to the blue ball because the brown ball is stationary. So your blue ball, since it's only moving in your x plane, right? Then in this case, we focus on your x plane. So we're going to write an equation for x plane only. So this is equation for x plane. So we have the mass of the blue ball times its velocity equals, so that's equal to your this now, which is the mass of the blue ball after collision. Now, because we're moving in x plane, this velocity that is given is actually the velocity in both x and y. But we only want the x plane, so that means x plane is your angle is theta here. So your x plane is cos, right? So that's cos of your angle. So in this case, we have v1 f cos theta. So this here gives us the x component of your velocity. Plus, now our brown ball, it's your mass of the brown ball, m2 times, again, we're looking at the cos because we're looking at this x component of this velocity here. All right, so we get cos of the angle created. Now, so that's first, that's your x plane momentum, right? So that's the conservation of momentum in your x plane. Now to find it for your y plane now, for your y plane, we look that no object is before collision, none of these objects are moving in a y direction. So this is strictly in your x, and this is not moving. So therefore, before collision in your y plane, momentum is 0. Then after collision, we notice both moving diagonal, so they're going to have a y component. So again, this is just the velocity of your blue ball. So therefore, we need to find the y component, which is opposite to your angle. So that's sine. So that is v1f sine theta. And that gives us your y component velocity for the blue ball, right? Plus, now we see that this is a negative, and this is negative because this y component is acting downwards, right? And going down, that means your velocity is negative. So in this case, it's the negative mass m2 times v2f sine your angle, right? So v2f sine angle there gives us your y component of your v2 velocity. All right, so once you are given any of the values there, then you'll be able to complete the question, any question. So the first thing for momentum that's acting in both plane is that you generate your both equations, one for your x plane and one for your y plane. All right, so is that clear? All right, so no questions. So let's look at now some values given. So let's say that the two masses are equal, which is 0.06 kilograms. V1 of the blue ball is 2 meters per second. V2 F, so the brown ball velocity after collision now becomes 1 meters per second. The angle of the brown ball is 20 degrees Celsius. 20 degrees, sorry. All right, so the aim here is to find the V1 velocity after the collision. All right, so, and also V2F is 1, V1 is 2. So remember we had both equations. All right, so this is the first equation. There is your x plane equation. So this is your x plane equation. This here gives us our y plane equation. So for our y plane equation, we can bring over this here, right? So we get m1 v1 f sine theta equals m2 v2 f sine of your angle. Now m1 and m2 are the same from our question, so we can cancel both masses out. So we are left back with v1 f sine theta equals v2 f sine the angle, right? So we have v2, which is 1 times sine of your angle, which is 20, so which gives us 0.3234 meters per second. Right? And that tells us that V1 cos theta gives us this value. Right? So in that we have that we now have that V1 sine theta. So now we go now to the x plane and we generate that V1F cos theta is equal to V1 minus V2F cos of your angle. We substitute the values and we get 1.060 meters per second. So what we've just found is that we found your y component and also your x component of V1. Right? So this is your, so this here sine is your y component and this one is your x component, right? And then now we can go ahead and find, so because we have this and we have this, if we divide both, so if we're supposed to divide both v1f over v2, the v's get canceled, sine theta over cos theta gives us tan theta, right? And that's equal to the 0.34 over the 1.060. Right? So we can get the angle created to be 17.88 degrees. Now that we have the angle, we can substitute to find V1F, which is the value 0.342 over sine theta, and sine of theta is 17.88, and we get V1F to be 1.11 meters per second for the final velocity of V1 object. All right, was that clear? All right, so in all cases, it's the same step that we'd use. All right, so we're going to look at one example when we resume after this break. So just going to restart since the time will soon expire. All right, so let's look at this question here. So it says one ball is shot east at 2 meters per second. A second identical billiard ball is shot west at 1 meters per second. The balls have a glancing collision not a head-on collision, deflecting the second ball by 90 degrees and sending it north at 1.41 meters per second. What are the speed and direction of the first ball after collision? All right, so the first thing here is, let's do a little sketch. So this is our first ball, and it's going to the east, right? So this has a velocity of 2 meters per second, and the next ball is going to the west, and it has a velocity of 1 meters per second. All right, so they're both identical, so that means they both have the same mass, so we're just going to call them M. So that's before collision. After collision, it says that the second ball, so the second ball, it moves north at 1.41 meters per second. All right, and then the second ball is unknown. We need to know where it is going. So we need to find the velocity and the angle theta direction. All right, so those are the two things that we need to find for that ball, which is your first ball. All right, so to not get confused, we're going to call this M1 and M2, but to know that both are the same. All right, so this is M2 and this is. All right, so the first thing we're going to look at is our x-plane motion. So we go to the x-plane momentum before, which tells us that it's M1, and let's call that V1, plus, all right, so it's plus, but because M2 is going to the left, the velocity makes it negative, so it's minus M2 V2 equal, we notice, so let's say that M1, all right, it's going at an angle, so we're going to say it's X, so it is cos theta, so it would be V, so it's M1 V1 F cos theta, right? And then M2 is going horizontal, it's going vertical, so there is no horizontal component, so that is 0, right? So let's substitute the values. So we have M1, V1 here is 2, so it's 2M1 minus V2 is 1, so that's just M2 equals M1 V1F is unknown, cos theta, which is unknown. So this, remember, the masses are the same, right? So therefore we can call this that this is 2 minus 1, which is 1, so it says M1 equals M1 V1 F cos theta, and again these two masses are the same. Alright, so therefore we get 1 because we cancel out the masses. So we get 1 cos theta. Alright, so that's 1. So the x component equation is now simplified to that portion. Alright, so let's write it here so we don't forget. So 1 is equal to V1F cos theta. Right? Now let's look at the y component. So the y component now, we notice that for both x and y, there is no y component before collision. So that means before collision, that's 0. Then after collision, the M1 is still unknown, so it's M1 V1 F. Now this becomes sine theta, right? And then M2 is going directly north, so that's plus M2, right? And we know that sine of 90 is 1, so it's basically 1 times its velocity, which is just 1.41. right? Because sine 90 degrees is 1. So we have that there. So we can take this one over. So we get negative m1 v1f sine theta equals to 1.21 m2. Alright, so remember again, the m's are the same, so they can cancel. Right, and if we divide by the negative 1 to get rid of negative here, we get that f v1f sine theta is equal to negative 1.41. Right, that gives us the y equation. So we have an x equation, we have a y equation. Right, so now we can divide both. Right, so let's simplify now. So now we have that our y is negative 1.41 equals v1f sine theta. Right, so now we can divide. So we're going to divide y over x, and that gives us, so that is negative 1 point equals v1f sine theta over 1 equals v1f as cos theta. Right, so we get negative 1.41 here. This v1f cancels out. Sine over cos is the same as tan theta. So therefore, theta is equal to the tan inverse of negative 1.41, which is equal to, so theta is equal to negative 54.65 degrees. Now, what the negative tells us is that the angle created is in the negative quarter. Right, so this is a positive. Right, so if the angle is negative, then that means the ball actually is going in this quarter, could be this one. Right, so we're going to check. So the negative just tells you direction. So the angle created between the horizontal will be 54.65 degrees. So now we have the angle, we can find what the V1F is. All right, so we can use, let's use X component. Right, so the X component says that 1 is equal to V1F cos theta. So 1 is equal to V1F. Now cos theta is 54.65, right? So basically V1F is equal to 1 over cos 54.65, and that's equal to 1.73. 1.73 meters per second. All right, so is there any questions for this one? All right, no question. All right, so we're going to look at the last thing, which is one last question, which is this one. All right, so I'm going to give you just some time to try by yourself, and then we go through it together. See if you can get some answers, and then we work it out and see what our answers will be. All right, so question 3, let's give it some attempt, and then we look at it together. All right, let's go through it together. The time will soon finish. All right, so it says peregrine falcon often grabs their prey from above while both falcon and prey are in flight. A 0.80 kilogram falcon flying at 80 meters per second scoops down at 45 degrees from behind a 0.36 kilogram pigeon flying horizontally at 9 meters per second. What are the speed and direction of the falcon now holding the pigeon immediately after impact? Right, so we know that this is an inelastic collision, right? And we're asked to find the velocity and the angle after they are together. All right, so remember the first thing we do is to separate our planes. So let's go with our x plane first. So in our x plane, or our Falcon mass, so it's m of your Falcon times the velocity of the Falcon in the x plane. It's moving for that 18 is diagonal. So in your x plane, that is cos. So that is your VF cos theta, right? So that your x plane is going to the right, so that's a positive, right? And then for your pigeon, it's going to the right as well, so that's MP. It's only moving to the right, so it's not diagonal, so that is just EP equals to the momentum after, right, which is both being added, so it's MF plus MP, right, times V, so V common F, and it's cos the angle, right? So we get that for your X, right? We substitute the values. The mass of your Falcon is 0.8, so 0.8, and we have F, which is 18, so that's 18 cos your angle there, which is 45, plus your mass of your pigeon, which is 0.36. The VP there is 9, equals to the sum of your masses, which is 0.8 and 0.36, which is 1.16 times VF unknown plus your angle, which is unknown as well. All right, so substitute. So let's simplify this first. So if we simplify the left-hand side, the cos 45 is 0.707 times 18 times 0.8. All right, we get 10.18, and then 9.036. So on your right and your left hand side, this is all equals 14.22 equals the 1.16 VF cos your angle. We can divide by 1.16 on both sides. So therefore, we get 12.26 equals the VF cos your angle. So that is your simplified equation for your x plane. Right, so let's back up here. So we can put this right here. 12.26 equals to VF cos angle. Right? So now let's look at your y, because there's nothing there we can find. Both things are unknown. So for your y now, so for your Falcon again, that is your mass of your Falcon times your velocity. It's sine now, so it's that's VF sine theta. Right? For your pigeon, it's not moving in your y, so that means that's 0 before collision. Then after collision, it will be your masses of your pigeon and your Falcon times the VF sine theta. All right, so we substitute. This is 0.80 times 18 sine 45. This is 0. Add these, we get 1.16 times VF sine your angle. All right, so on this side we get Sine 45 is the same 0.707 times 18 times 0.80, and we get 10.18 equals 1.16 VF sine angle divided by 1.16 on both sides. So we have VF sine theta is equal to 8.78. All right, so now we have both simplified equations. We can find something that's unknown. All right, so let's put both together now. So for y is 8.78 equals VF sine angle. All right, so now we can go ahead and divide y by x. So your y plane value by your x plane value. So y by x would be 8.78 equals VF sine theta divided by 12.26 divided by VF plus angle. Right, so VF cancels, and 8.78 divided by 12.26, and that gives us 0.716 equals sine over cos is and the angle. So the angle there is tan inverse of 0.716, which is 35.60 degrees. So that's our angle there. Now that we have our angle, we can use any of those equations to find VF. So let's use the x1. So it's 12.26 equal to VF cos 35.60. Therefore, VF is equal to 12.26 over cos 35.60, and that gives us 15.08 meters per second. All right, so is that any close to your answers that you got? All right, so that's it for today, guys. Thanks very much for coming, and I hope you understand something about momentum as well as for projectile motion. All right, so see you guys next time.